Monday, but hopefully Wednesday. So 2.7 and 2.8, the derivative, finally. Okay. We know two concepts so far that are major concepts, and they will move on with us. One is the concept of the limit, and the other one is the concept of the difference quotient. We want to be able to find an expression function, of course, that gives the instantaneous rate of change at any point. Now I'm going to use a word that I will have to explain, where the function is differentiable. That's a Scrabble word for you. Okay. So you can say, wait a minute, what are you talking about? You said the limit, I understand. I've been working on almost a month on this. Done. You're talking about the difference quotient, I got it. We worked on several functions. I know how to determine the difference quotient. But what are you saying now? So when we talk about something like this, the derivative is another function. So I have a function and I want to find its derivative. First of all, why? Why do I care about the derivative of a function? Because I want to be able to find the instantaneous rate of change for any function at any point where that rate exists. By differentiable, we mean where that rate of change exists. When it does not exist, I will explain. So, in other words, I travel from Baltimore to New York. So here's Baltimore, here's New York. I travel roughly 200 miles. And I have a function that gives me the distance. Let's say I have a function. I'm just going to say it's 1/2 x squared plus 2x minus 3. This function gives me the distance that I cover. I start here at 7 a.m. and I have no idea when I get there, but I know I start at 7 a.m. I know I have to cover the distance of 200 miles, and this is the function that gives me the distance. While driving, you call me and you ask me two things. I want you to tell me, Professor, after you get there, give me the average rate of change of distance with respect to, that's how lazy people write, with respect to time. And I'll say, no problem. I cover the distance of 200 miles in 6 hours, and I'll tell you what this is. And that will be in miles per hour. That's easy. But then you call me at 8 a.m. and you ask me, what is your instantaneous rate of change? Which is speed, right? This is the speed. By average rate of change with this distance with respect to time, we talk about speed or velocity. So what is your instantaneous rate of change or speed? or velocity of distance with respect to time. But this I cannot give you without the function, right? I have the function. Unless I look at the odometer and I'll say 63 miles per hour. So I can give it to you if you call me, and that instant I'll tell you, okay, I'm looking at my odometer and I see this. This is what we call by instantaneous. Now, if I have the function and find its derivative, I don't need you to call me at any particular time. You can just say time 2 hours. I'll plug it in the derivative and I'll give you the rate of change. Then you say time 3 hours. I'll plug in the derivative and I'll give you you don't have to call me every hour. So the derivative function notation, first of all, f prime. What does it give again? It gives the instantaneous rate of change for any function. It doesn't have to be a distance function. Any function, I can determine the instantaneous rate of change. And now again, let's come back to this, where the function is differentiable, or in other words, where it has a rate of change. Okay. So let's look at our function from before, in which we had right here point P, and then we had point Q, and we really wanted to determine the slope of the tangent line at that point. We wanted to find the slope of tangent at P. We didn't care that much about the average rate of change between Baltimore and New York. You really wanted me to give you the rate of change at any point in time, the instantaneous rate of change, the slope of this line. So the derivative will give the rate of change or the slope of the tangent line at any point where the function is differentiable. Where will a function not be differentiable? Not differentiable. Where this function does not exist, this is what it means. F prime of x is dne. At any point where I cannot determine the slope of the tangent, if at any point on a graph I cannot determine the slope of the tangent, at that particular point the derivative does not exist. Okay, so let me give you the examples and then I'll define the derivative. And then I will make the connection between these two concepts and why we studied them. Okay, so let me give you the situation in which we cannot determine the slope of the tangent. Which page am I? I think I'm on 9. Yes, I'm on 9. Okay. So again, not f of x, not differentiable, where I cannot determine the slope of the tangent. Or it's not unique. One situation, this function is not differentiable at a because it's not continuous. Period. Done. If it's not continuous, I cannot determine at this point. There are two tangents. And the tangent has to be unique and have one slope, not two different tangents. Okay, here's the second possibility, when a function does not have a derivative. Corner. Same reason. At this point, it has this tangent, and it has this tangent. It's continuous, but it has a corner. Another possibility, something like this, like between two teeth, so to speak. This is like a vertical tangent. Vertical tangent. This is called a cusp. And the actual vertical tangent, they are the same. You don't have to call this one vertical tangent, but that's what it is. So here it is. Vertical tangent. The vertical tangent has slope undefined. Vertical tangent has slope undefined. Here, two different tangents. Here, two different tangents. Okay. Good. So let's talk about this f prime. What is it? Well, it's exactly what you would have expected, maybe, hopefully. These two together. Limit as h approaches 0 from f of x plus h minus f of x divided by h. That's why we talked about this. That's why we talked about this. And now these two concepts together give us the first derivative, or the derivative function. Derivative function. Whenever this function exists, it will give us the instantaneous rate of change of the function itself. Give me any simple function so we can determine its derivative, and then we'll stop. I will suggest, and you pick, either a simple function that is the simplest quadratic. I would like to do both today, but I don't think we have time. Let me see what is it. So 4 minutes. We can do the other one next time. So please choose. We're going to use the definition. This is the definition of the derivative function to determine the derivative of either one.
Can we do x squared?
Let's do x squared. Very good. Okay. Page 10. Good. So let's determine the limit. So f prime of x. Because it's just simple, I wanted to say do it this separately, but there is no need. So limit as h approaches 0. Can anyone tell us how to write f of x plus h?
X plus h squared.
Very good. Can anyone expand? Remember 3 things here, right? For the difference quotient. All terms without h must disappear. H from the denominator must disappear. But now I no longer will say that h must be left in the final form, because now I will apply the limit. Good. So can anyone expand that for us?
X squared plus 2xh plus h squared.
Thank you very much. Of course, h in the denominator must go away. What will be the next step, please?
You factor h out of the term.
Good. 2x plus h. Now please apply the limit and tell me the rate of change of x squared at any point in time on the graph of the function, or the instantaneous rate of change.
So just 2x?
That's it. So please remember moving forward, x squared prime equals 2x.